In this lecture, we're going to talk about how to use the Laplace transform notation of a system to do some quick calculations to determine how the system responds at different frequencies. So what I've given here is an example of a linear system, and if we analyze this system, we can see that it has 1, 0, and 2 poles. So the 0 is going to be located at s equals -10, and that's in units of radians per second. And the poles are going to be located at s equals -1000 and s equals -1 million radians per second. So first thing I'd like to do is get a quick idea of what the transfer function might look like if I were to plot the magnitude of h of j omega. And we've actually already talked about how to do a Bode plot, so we should have a pretty good idea of this. But just to remind you, we're going to start at a frequency of 0, and then we're going to increase our frequency bit by bit. And whenever we reach a 0, we're going to increase our slope by 20 decibels per decade. And whenever we reach a pole, we're going to decrease our slope by 20 decibels per decade. So for example, if I were to draw myself an axis here, we know that, let's see, at low frequencies, we're going to start at whatever, some constant value. And then when I reach s equals 10, I have a 0. And that's going to cause my slope to increase by 20 decibels per decade until I reach my next milestone, which is 1000. And that's going to cause my slope to decrease by 20 decibels per decade. Well, if it was plus 20 and I decrease it by 20, now it's going to be flat. And that's going to continue until I get all the way out to 1 million rads per second. And once I get there, the slope will once again drop to -20 dB per decade because I hit another pole. Okay, so generally speaking, that's what the Bode plot looks like. What I haven't worked out yet is what the y values are. So in other words, I don't really know what values to put there or what values to put here. I just know this is the shape. So let's see if we can work some of that out. So an easy way to start might be to say, well, let's find the let's see, how does this system respond. So what is the system response to a cosine at, I don't know, let's try 10,000. So you'll remember from the previous video that we said that if you take the Laplace transform and you limit yourself to the j omega axis, you get the Fourier transform. And that's important to remember because the Fourier transform is what tells you how the system responds to different cosine inputs. So in other words, I'm just going to take my system and I'm going to say, instead of h of s, let me just for a moment think of it as h of omega. And I'm basically just going to write the exact same thing, but instead of using s, I'm going to write it using j omega. And generally speaking, you don't always have to go to all this trouble to write it all out like this. I'm just doing it for the sake of trying to make this as obvious as possible. Now, if I wanted to find the magnitude of h of j omega at 10,000 radians per second, then I would need to do the following. I would have to take the magnitude of the numerator divided by the magnitude of the denominator. And the magnitude of the numerator is going to be the real part squared plus the imaginary part squared, square root. So it's going to be 10k squared plus 10 squared square root, and that handles the numerator. And the denominator is going to be 10k squared plus 1000 squared square root times, oh my goodness, almost done. Oops, I can see here I made a mistake. Instead of S, that should have been j omega, and so that's going to be my frequency of interest, 10k squared plus 1e6 squared square root. And now I have a giant gross math problem on my hands, but I actually went and worked it out ahead of time, and I got that my answer was 0.995. Okay, so it's about a gain of 1. Now, that was the hard way. Let's look at the easy way. To remind you, you might have seen this before, but let's go back to this. Now, for the easy way, let's remember that when you're dealing with a frequency of 10,000, that 10,000 is much, much bigger than 10. It's much, much bigger than 1,000. And it's much, much smaller than 1,000,000. So therefore, if I take that transfer function and go term by term, I have 1e6. Okay, I can't do anything about that. But now if I'm looking at these two terms, the j omega and the 10, I know that the 10,000 is much bigger than the 10. So really the magnitude of that is essentially just the omega, right? It's so much, the j omega is so much bigger than the 10 that I can effectively ignore the 10, and then the magnitude of j omega is just omega. So omega is 10,000. Now I go to the denominator, and it's the same story. In a contest between 10,000 and 1,000, the 10,000 is much bigger. So we can basically ignore the 1,000. And when we do that, we're left with the j omega, whose magnitude is just 10k. And then finally we have this term, where we have the j omega plus 1,000,000. In that case, the 1,000,000 wins, so it's 1e6. And look at this. Everything cancels. Okay, so 10k cancels, 1e6 cancels. And what am I left with? I'm left with a gain of 1. Okay, now 1 is my estimate, 0.995 is my actual value. And you can see that my quick and dirty method got me an answer that was accurate to within, to better than 1%. Okay, so that's not too shabby. So just something to keep in mind is that this trick only works as long as these values are much, much bigger or much, much smaller. And generally the threshold for that is a factor of 10. If they're within a factor of 10 of each other, then you actually need to go ahead and arrange the math, or do the math. Now, next thing to remember, a gain of 1 really corresponds to a gain of 0 decibels, right? Because 20 log base 10 of 1 is 0. So that means in these midband frequencies, we have a gain of 0 decibels. Okay, what about down here? What gain do you think I have down there? Well, there's a couple different ways I can do that. I can either go back to my transfer function and substitute in, instead of omega equals 10,000, I could substitute in a really small frequency, like omega equals 0. And if I do that, I'll find that my gain at omega equals 0 is about, let's see, it should be about 10 over 1,000, which is 1 over 100, which is 0.01, which is also negative 40 dB. So this value here is negative 40 dB. The other way to come to that same conclusion would have been to say, look, I know that this point here is 0 decibels, and I know this line slopes at 20 decibels per decade. So all I really need to know is how many decades there are. And in this case, there are 2 decades. Okay? And the reason I know that is because a decade is a multiplier by 10. So if I take my original frequency of 10, multiply it by 10 once, that's 1 decade. By 10 a second time, that's a second decade. Then I get my final value of 1,000. Okay? So if this is 20 decibels per decade, if I go 1 decade back to 100, I know I'm going to have a gain of negative 20. And if I go another decade back to 10, that's going to be another 20 decibels down from, so I was 0, -20, and now -40. Okay, so either way it works out to the same thing. Generally speaking, the number of decades can be calculated as the log of the ratio of two frequencies. So in our case it would be log base 10 of 1,000 over 100, okay, which is 2 decades. Now, two final things I want to tell you. The first thing I want to do is I want to look at the step response of this signal, and I've actually calculated the step response of this signal ahead of time, and this is what it looks like. Okay, this is the step response for this signal. Oops, let's try that. So step response, and I want you to notice something. The first thing I want you to notice is that it doesn't oscillate. So you'll notice there's nothing here that looks like that. Okay, there's no oscillation. Why not? Well, to get the answer to that, we have to go back to our poles and zeros, and for a moment we're just going to focus on the poles. Okay, this conversation doesn't include the zeros, it just has to do with the poles. If I look at the poles, both of them are real. And because both of them are real, what we learned is that there's no oscillation. In order for the poles to oscillate, there needs to be a j omega term, but there is no j omega term. So because I have two real poles, I have no oscillation. All right? The other thing I'd like you to notice is that if you pay very close attention, this does not decay to 0. Now when I first saw this, this kind of caught my attention, and it took me a minute to figure it out. I thought maybe I'd done something wrong in MATLAB, but it turns out that it actually makes sense after I thought about it for a while. So let's remember what a step input looks like. Okay, so this is the response to the step. So a step input means first I had nothing, and then I had an input whose value was 1. Now for all intents and purposes, sorry, this is time over here. This is basically a constant input. Okay, because it doesn't change. And that's synonymous with frequency equals 0. Now, what does this system have as a gain of frequency equals 0? Well, if we come back here, we've actually calculated that already. At a frequency of 0, I have a gain of 0.001. And sure enough, this value here, I checked it in MATLAB, doesn't decay to 0. It actually decays to 0.001. Or sorry, 0.01. And the reason for that is because this system has some gain at low frequencies, and that's what you're seeing. It doesn't have a gain of 0 at low frequencies, it has a gain of 0.001, and that's why you're seeing the step response retain some of its value at the output, which I thought was pretty cool. Alright, in the next few videos we'll continue with our investigation of poles and zeros, and we'll try to work out in a little bit more detail what poles and zeros tell us.